for the second problem in the set, we have the following situation. We have a container full of water, and we consider a thin layer of water up at the top, a layer of mass m. Okay, now in the problem, of course, you're given a mass here. We're going to symbolize the solution, and you can then work through the solution as given on the home page. But we have the thin layer of mass m here. Now, we're going to consider the potential energy change when this thin layer goes away. That is, the water is going to fall slightly and that thin layer won't be there anymore. Instead, there will be an equal mass m exiting at the bottom of the tube, exiting at the hole here. So we have a mass m exiting that's we think of as being this mass just an instant later when an equal mass exits. Of course, it's not the same water up here that exits down here, but it's an equal mass. And the system's potential energy then is going to change because we have more potential energy here than we have when the mass is down here. The potential energy change of a mass m as it disappears up here and effectively reappears down here is just negative mgh. Okay, because the distance from here to here is, of course, h. So the potential energy change, of course, is the product. Well, let's think back to potential energy. If we were to lift the mass back up, we would have to do work. And the work we would do would have to be equal to the force we have to exert times the distance h through which we exert it. How much force do we have to exert on a mass m? Well, mg, the weight of that mass, in order to raise it. So we take mg, the weight of the mass, which is the force we have to use to raise the mass, and we raise that mass distance h, and the work is going to be mgh. So that when the mass goes from here down to here, the potential energy change will be the negative of what it would be if we lifted the mass from here up to here, or negative mgh. So the kinetic energy change is plus mgh. Now the assumption of the problem is that no energy is dissipated. We can only say this because there is no dissipation of energy. Okay, over here we have a note that's essentially the same as this. The mass goes from here and is replaced down here, so the system potential energy changes by negative mgh when mass m escapes. Because every time a mass m escapes here, that top layer of water disappears, and we have that potential energy change. Now, the mass m will therefore exit with a kinetic energy which is equal to, well, the kinetic energy change is mgh. The kinetic energy of the mass when it was up here is presumably zero. We assume the container is large compared to the size of the hole, so that the water isn't falling very fast, so that the kinetic energy of this mass up here is effectively negligible, effectively zero. And we have then that the exiting kinetic energy is mgh, which means that 1/2 mv squared is mgh, and we easily solve this for v. We take the divide by 1/2 m, we end up with 2 over m times mgh, and then we take the square root, we divide the m's out, and we end up with a velocity equal to the square root of 2gh.